like to welcome you for a new episode of Conversations at the Center. I am Edouard Machery, Director of the Center for Philosophy of Science and host of this podcast. Today, our invited participant is my colleague, John Norton, from the Department of History and Philosophy of Science. John, would you mind introducing yourself?
Sure, I'm happy to be here. I'm a professor of history and philosophy of science. I work in a number of different areas. My early work was in history of physics, history of general relativity in particular. I've worked on a range of topics in history and philosophy of physics more generally. My more recent work has been on topics in inductive inference. I have a novel account of the nature of inductive inference as being governed by material facts as opposed to universal rules and laws. If you're interested and want to hear more about this, I have 2 books out. The Material Theory of Induction has been published in the BSPS Open Series, and I have a second book, The Large-Scale Structure of Inductive Inference, that will be published very shortly. You might find it interesting because one of the consequences of the material approach is that you cannot even set up the problem of induction, so the problem just goes away. My next project will be on empiricism.
Very good. So today our episode will be somewhat different from the previous one. So our past episodes have been focused on narrower, maybe more technical issues in philosophy of science. Today we will be rather focusing on a basic, fundamental question in philosophy and in philosophy of science, which is how do we know things? And in particular, how do we know things by means of science in comparison to other ways of knowing things? We have this episode because in 2 weeks from now, the Center for Philosophy of Science is hosting its summer program for undergraduates, PSP, the Pittsburgh Summer Program in Philosophy of Science. And we hope that our students will listen to this episode before joining us. So the basic question today is how do we know things and how do we know things by means of science? And as John mentioned, he's finishing a book, or almost finished, hopefully, or maybe, on empiricism, which touches, of course, on this question. So to get us started, John, what is distinctive in your view about knowing things by means of science?
An interesting question about which a lot has been said. And I have a very short and simple answer. The best science simply consists of a body of fact that is well supported by evidence. It is the commitment to strong evidential support. Always it'll be inductive support that is the distinctive thing. And what distinguishes the scientific enterprise is that is the idea that is pursued. Now, you might think that's kind of obvious, and what else might one think? But if you were to ask this in a more popular domain, I think you would discover that there's a different story out there. What's distinctive about science is that it is falsifiable. This is the Popperian account. I regret very much that this account has taken hold because it is not the right characterization. It has caused a tremendous amount of mischief. Anyone who has a crank theory can make the theory falsifiable by throwing in some factual statement that can be demonstrated to be false. So one can very quickly make something look scientific when it actually isn't. And there are reverse problems. If a scientist is hanging on too tenaciously to a theory that might ultimately be vindicated, they might fall foul of the accusation of refusing falsification. So that's the simple idea. Edouard, I know you have ideas on this as well.
Yeah, I mean, I tend to believe that science is actually quite diverse as a project. But I agree with you that in contrast to other ways of knowing about the world, or maybe other ways of forming beliefs, not all of them are ways of forming knowledge, but other ways of forming beliefs about the world, scientific hypotheses are always hostages to the way the world turned out to be. And I think this is a distinctive feature of science that has indeed been characteristic of what emerged in maybe the 15th, 16th century and possibly elsewhere in other parts of the world as well. So I tend to agree with you. I also think there are other aspects of science that might be quite distinctive, which is an effort to formulate often, anyway, in many parts of science, generalization, of some abstract representation of some of the processes that we are observing, trying to explain also the things we're observing by postulating things we do not observe. I think this is also quite a distinctive process aspect of science that single it out from maybe other ways of forming beliefs about the world.
There's I think a systematic difference between us in the sciences that we look at. You're more interested in the social sciences, and I'm interested in physical sciences. And I think things work out better in the physical sciences than they do in the social sciences. I'm not worried about positing unobserved entities like electrons. I think we have massive evidence for them. And I want to go back and just emphasize what I think the key thing here is. It's not that all of our science is hostage to experience. I want to see in good science that any particular proposition in the science has a definite evidential base. You ask me why I believe that electrons have spin a half, and I can tell you an evidential story. You ask me why I think energy is conserved in this process, and I'll tell you an evidential story. I wonder if things are as secure in the social sciences.
The answer is no, obviously. Now, I can tell you some story which will be connected to some facts that we can observe usually in an experimental situation in a lab. But the connection will be, I suspect, much more tenuous, and we will be relying on a host of assumptions, many of which haven't been really defended or supported. And I think that's one of the main contrasts with the sciences you are looking at and the sciences I am looking at, where the assumptions in your part of the world tend to be much better supported, much less conjectural than the assumptions that are made to connect somehow a very thin empirical basis in the lab to hypotheses about the functioning of the mind. So I think that's really an important contrast. I also suspect that the assumptions are often implicit in my part of the world. People aren't really quite aware of the assumptions they're making to connect hypotheses with the data or the evidence. Well, I think people are probably much more careful and much more explicit about the assumptions they're making, which is required to support them.
I wonder if the methods that are used in social science are trying too hard to copy the methods that might be used in physics. It is the case that all electrons have the same properties, and so you can very quickly understand the behavior of a large collection of electrons by looking at their individual properties. They're going to be stable over time. Does a similar sort of hypothesis work well in the social sciences?
So it has been actually in psychology or in cognitive psychology or cognitive science maybe one of the most fault line between two ways of doing psychology. On the one hand, you have what is sometimes known as the first discipline of psychology that assumes that at some level of description, pretty much all of us are the same. And that now, what is the right level of description is a little bit of a mystery. And then there's a second discipline of psychology that focuses on human differences, and that is not committed to the idea that there's a level of description at which we're all the same. I'm afraid that the first discipline, the one that tries to identify invariances among human beings or similarities at the very least between us, has not been fully successful, and in fact has not been dealing well enough with diversity. You can just see that often when you run a statistical test where diversity all end up, or the variation all end up in the epsilon, in the measurement error, as if all variation was just measurement error, which is just an assumption that is almost never tested. The assumption, the variation could be actually be much more systematic and not just be the way somehow different ways of interpreting the measuring instruments, of reacting to the measuring instrument. So I think that's right. People have been assuming that there is great similarity among human beings, and whether this assumption is correct is far from being clear.
I would wonder if the same applies in economics. The thing that seems to be true about economic systems is that they keep changing, and we keep adapting our theories to the last thing that happened, and then a new circumstance comes about. Is the replication crisis connected with this in any way?
So it's one of the possible reasons for why a large part of psychology and maybe the biomedical sciences fail to replicate. Because, of course, if your experimental units, human beings or groups or whatever they might be, differ from one another, when you're going to redo your experiment, there will be variation that is just a reflection of the underlying variation.
Perhaps you should just state what the replication crisis is.
This is actually a good point, John. So for our students and for those of you, for the listeners who have not been focusing on psychology over the last 15 years, about 15 years ago, social psychologists first, but then other areas within science, including the biomedical sciences, found that a large part of the studies, the empirical and experimental studies that happen to be published, do not replicate when they are redone. That means that you redo the experiment with often new participants, and you do not get the same result as you got in your first study. And while we should have expected some amount of unreplicability for various reasons, false positives are unavoidable, and false negative in the replication, the degree, the proportion of unreplicable results in the published literature came as a shock for psychologists, people working in the biomedical sciences, and in other areas, in ecology, for example. Maybe in a famous paper, only a third of the published paper in psychology happened to be replicated. And you might think psychology doesn't matter too much, but the same is true of oncology, the study of cancer. A recent replication study suggests that at most a third of the papers published in oncology in fundamental research replicate. So it's actually a very large issue.
Can I check whether we have a common ground in the following form? I'm an empiricist. I think we can only learn contingent facts in the world from experience of the world. And I'm assuming we agree on that level. The question then becomes, how do we go about doing it, and how reliable are the methods that we're using to infer from experience? Let me mention a distinction that I'm working on when it comes to empiricism. Traditional empiricism in philosophy has been a highly skeptical thesis. The idea is that what we learn of the world, we learn from experience, and experience is in fact all we learn. We only know what we experience. I'm calling that big E empiricism. And you'll find the older traditions in empiricism tend to look like that. Sometime around the beginning of the 20th century, there was a bit of a shift. I think Hunter Eichenbach might have been one of the leading thinkers who participated in this shift. There was a softening. There was an idea that you can actually learn a great deal beyond experience. There are electrons, for example. I'm calling that small e empiricism, and that's the sort of empiricism that I want to defend. My sense is that you're definitely happy with big E empiricism, or at least insofar as we learn from experience, but you are much less happy to make the steps to what we learn that is beyond experience, because you've seen too many lofty castles fall to dust.
I think that's probably right in psychology. In many ways, I like the way you put it, because I feel I've learned that about some aspects of the social sciences. I was extremely trustful, extremely willing to take the social sciences at their words when I started doing philosophy of science. And the replication crisis came as a shock for me. It's, one might say that it woke me from my dogmatic slumber, to paraphrase Kant. And now I've actually become much more careful about taking the theories that psychologists, neuroscientists, social scientists, and economists, and many other people in this area are actually developing. So I think that's entirely true.
So you don't trust science?
I'm afraid I don't think trust is a relation we should have to science. Let me qualify that, however. So some areas of science and maybe some research traditions have settled science, and those definitively deserve our trust. So, human beings or human animals more broadly have a common ancestor. Settled science. There are atoms, settled science, and so on and so forth. So there are parts of science that are really well settled, but they tend to be quite old, and they have been extremely tested in many different ways. They've been the basis of technological invention. So we have a lot of grounds to actually treat them as trustworthy. I think for the rest of science, we should not relate to it as we do relate to someone we love, as we do relate to an expert. So trust isn't quite the right relation to much of science. Does not mean we should ignore it. That would be exactly the wrong answer. Science is wonderful. Science is the best way to learn about the world. But we should not treat it as if it was some form of oracle. And I think a degree of skepticism, to come back to a theme you mentioned in the empiricist tradition, is essential, in fact, not for the whole of science, but for many areas of ongoing and maybe even quite recent science.
I think we're agreeing on matters of principle here. I said that the best science is the collection of knowledge that is well supported evidentially, and we're looking at sciences that have weaker support. And if they're not well supported, then trust is not warranted.
I think that's exactly right. And I think, but what I've learned, and I think probably what we have learned, is that there's more areas of science that turn out to only look to be well supported. There's an enormous literature, enormous data, conferences, publications, theories that are apparently tested against the fact. They're not just cast in the sand. But as a matter of fact, the support is much more illusory than it really is, and for various reasons. I mean, we mentioned diversity of individuals or groups. That's one reason, but there are many other reasons for why the evidential support is less solid than it might first appear.
Now, I'd like to tell you that in physics, my area, everything is wonderful. But I'm afraid also there are corners of physics that I simply do not trust.
I had a question for you about that exactly. So which part of physics do you think are in a similar ballpark and a similar situation, and why?
Yeah, I see two sorts of areas in physics where things come unstuck. One of them is when there's simply a deficiency in the evidence. If you look at work in modern cosmology, there seem to be two wings of work in modern cosmology. One of it is heavily informed by the evidence. We're getting massive amounts of evidence from the new telescopic scannings of the heavens, and I think this is science at its best. You would look at the Hubble crisis at the moment as an example of that. There are ways of measuring the rate at which the universe is expanding, and if we take measurements on distant galaxies, and if we take measurements that come from the cosmic background radiation, we end up with numbers that are too far apart to be compatible. This is science working the way it should work. We have the evidence, and it's telling us that there's something wrong in our theories, and we need to work harder. But then when you go back to theories about the very, very early universe, multiverse theories and the like, there's a paucity of evidence there. That doesn't mean that cosmologists don't say anything. They say a lot. But it's wild speculation, and it often tends to get reported as facts that we have discovered. Very often we have not discovered anything at all. There's just been a cosmologist somewhere who had a clever idea and got the paper published, and then the office at his university has pumped it for the press and maybe taken off qualifications and the like. String theory is another example where notoriously we have no novel evidence for string theory. String theory works terrifically well when it's picking up everything we already know, but we've been unable to have an experiment that would say where string theory goes beyond what we already know, and telling us that those things are improvements. Then I'm afraid to say there are just cases where people think sloppily. I don't say that lightly because it's been a major theme of my research for the last 20 years. Physicists love to talk about the connection between thermodynamic entropy and information. And as far as I can tell, the results there are largely wrong. They depend upon people just finding similarities in formulae. The formula for entropy, for those of you who know it, is P for probability multiplied by the logarithm of P, and then you sum or integrate. And there's a tendency whenever the formula P log P pops up for somebody to say, aha, entropy. If you know some statistics, you'll know that P log P represents a parameter of a distribution that is often called the entropy. But that doesn't mean it has anything to do with heat. So yes, there are problems across the board, and we need to be forever vigilant.
So I had also another question. So we talked quite a bit about the role of evidence in science, about the fact that the evidential support might vary across discipline, and that trust might be calibrated to how much evidential support is available. Now, some parts of science look a little bit less empirical than others. And I have two in mind. The first one you've worked quite a lot on. The second one, to my knowledge, you haven't worked on. So the first one is thought experimentation. So the large part of science, some parts of science, I should say, involves formulating thought experiments, including at crucial junctures of scientific progress. But thought experiments don't really look kind of like an experiment in some ways. That's why they're called thought experiments. The other part is mathematics and the role that mathematical knowledge maybe plays in the best parts of science, including in physics. So do you have thoughts about either of those? I know you have thought about thought experiments because you've worked extensively on it.
Well, those of you who are coming to the summer school will have a morning with me when I'll talk about my views on thought experiments. I have a very simple view. There's nothing magical about a thought experiment. This contradicts an intuition that many people have. There's this idea that somehow you can get a result from a thought experiment that you can't get by other means. In order to understand why they would think that, you need to work through a compelling thought experiment. They often have a moment when you have this aha reaction and suddenly you see something that you didn't see before. My friend and colleague Jim Brown, formerly of the University of Toronto, thinks of that as a moment at which the window to the Platonic world of forms has opened and you actually are gazing upon the forms momentarily and thereby being informed. I think this is just mistaken. I think thought experiments are merely picturesque arguments. They can do nothing more than an ordinary argument can. So the way to evaluate a thought experiment is to treat it as an argument. A good thought experiment is a good argument. A bad thought experiment is a bad argument. Mathematics is much harder. Right? As long as we're talking about simple mathematics, arithmetic and the like, I have no hesitation in just saying we are pursuing the consequences of definitions. It's just a matter of logical reasoning. Things get more difficult when we start to get into abstract, higher level mathematics. So to be concrete about this, any of you who've done some advanced set theory will know the problem. There's a theory of sets, the Zermelo-Fraenkel set theory. It turns out that the very notion of set itself is a difficult notion to understand. You cannot say that a set is just any collection of things we care to throw together. Works as long as we're looking at a finite number of objects. But once we deal with infinities, you get into a lot of trouble. This was the basis of Bertrand Russell's paradox, the paradox of the set of all things that are not members of themselves. I won't go into the details there. So what replaces this naive idea about sets is an abstract theory of sets whose axioms were laid out by Zermelo and Fraenkel. And we don't say what a set is, we say what their properties are. And in the middle of it is an axiom known as the axiom of choice. It says there exists a certain sort of set that we don't know how to construct. And when we're dealing with stuff at that level, I just don't know what to think. I think there are deep problems in foundations of mathematics that our colleagues who work in philosophy of mathematics will struggle with. If you ask me, are there choice sets? In other words, do the sets that are posited by the axiom of choice exist? I'll say, I just don't know.
I think this attitude toward mathematics is actually quite common. I do feel mathematical knowledge, to the extent it's really knowledge, is really one of the most mysterious things that we philosophers of science or philosophers have to be thinking about. So I myself don't really have any idea about how to think about this question. I wanted to come back for a second to what you said about thought experiments. I suspect you would want to say the same thing for modeling what we can learn from models, right? That they're in no way similar to an experiment. They're in a way just exploring the consequences of the assumptions we've made, or do you distinguish modeling from thought experiments in this respect?
Yes, a model is something different. I think of a model as something like an idealized simplification of the system of interest, and it is useful to us insofar as the consequences that we draw from the model still lie within the things that are properly attributed to the system of interest. I haven't thought terribly much about models. There's a large literature out there, and I've not been able to come to any really comfortable sense of where I want to place myself in this literature, beyond the rather simple characterization I just gave. But I should ask if you think about models and where your view is.
So I think a model is just an abstract representation of a situation, or a class of situations, and as a matter of fact, what we learn from models is just what we learn from any representations of a theory. I think a simulation, which is also what I had in mind when I asked you the question, is just an implementation of a set of assumptions about the world. And in that respect, they are quite dissimilar from an experiment. From a simulations, we basically learn things about the assumptions that we have put into the simulation, which is, of course, learning something, but it's not learning about the worlds that are represented by the assumptions. It is learning about the assumptions themselves. Now, if the assumptions are true, we are indirectly learning about the world, but by that, we don't really know whether they're true.
Well, the old idea about this has been that simulations are essentially reasoning from the assumptions we've made, and they pale in comparison to real experimentation. But the work of Wendy Parker, I think, has forced at least me to shift from that view. She pointed out, I think, two things that require a softening of that very hard distinction. The first thing is that no experiment, no material real experiment, is ever free from assumptions. So unless you're actually experimenting on the very thing itself of interest to you, you have to assume that the thing that you're working on is relevantly similar to the one that interests you. So Wendy's area is meteorology, and she's pointed out that it's very hard to get a physical system that will replicate the properties of the climate well. Now, you might think, what's the problem? We just have a sphere, and there's a fluid on it, the air, the compressible air, and has a certain amount of moisture in the air, and it's all spinning and swirling around. So we just need to build a system like that, and then everything will be fine. But the difficulty is that it's very hard to scale that down to a small laboratory such that you can get reliable results that can be ported back to the big system. Water swirling in a bucket is certainly very, very far from it. So you have to realize that simulations and experiments both rely on assumptions. Now, the next thing that happens is you can actually build the assumptions into the simulations so they become as good as real experiments. The striking example has been the design of airplanes. It's now no longer necessary to put a model of an airplane in a wind tunnel. The simulation of the aerodynamics of an airplane design now is so good that it's just not needed. You can just consult the computer simulation, and you'll know exactly as much as you would get out of the wind tunnel experiment. So I think there's room to bring the two extremes closer together.
Yes, I mean, everything you said strikes me as right. There are, of course, similarities between an experiment and a simulation. I think that should not lead us to overlook the differences, which I think relates to what is under our control and what is not under our control. I think there are an aspect of the world that's not under our control. That's not under our control when we're doing an experiment. While when we're doing a simulation, in principle, we can set up everything one way or the other. And I think that makes an important difference from what we can learn from one and the other. Now, and you're right that if the principle of the simulations are true, then we don't need to intervene on the world to know about the world. It's just because the principle of the simulations are an accurate representation of what the world is. But that does not make them identical, as I believe.
No,
yeah.
I agree, but perhaps I can say this. We need to look at the cases one at a time, take them on a case-by-case basis. I prefer the weather forecasts that come from computer simulations, but if you're asking me whether some new alloy will be superconducting at such and such a temperature, go and do the experiment, go and do the measurement.
That's right. So I think we've already been talking for nearly half an hour, but maybe to conclude this exchange, we should move a little bit away from science, and since we're both philosophers, what do you think of philosophy? Is that a source of knowledge? In what way? Is it empirical in the way that science is empirical? John, what do you think?
This is a sore point with me. The difficulty that I'm seeing in much of present philosophy is the illusion that mere thought alone can bring about interesting factual statements of the world. Now, my criticism of people trying to do this is fairly well entrenched. I'll give you two examples of it. I've worked fairly extensively on notions of causation. There is this idea amongst philosophers of causation, amongst metaphysicians of causation, that that it is a factual matter that the world is fundamentally causal. There is some kind of causal principle that is governing the world, and the individual sciences merely have the work of figuring out what the expression of that basic principle is in their individual sciences. I think this is a mistake and an illusion. And to support that, I've reviewed the history of attempts to state what that fact is. And philosophers and metaphysicians have simply failed routinely for 2,000 years ever to come up with a statement that didn't need subsequently to be corrected. So my view is that things are connected in the world in ways that go beyond experience. I'm not a Humean skeptic, but I don't think that causal metaphysicians have anything to add to it. I have a similar critique of notions of possibility and modality. Modal metaphysicians seem to pull from nowhere deep truths about the world. So then, what is it that philosophers do? In what way is our work useful? Well, I've just given you two examples of what I think is useful philosophy. There's always a pull between people who want to work creatively in philosophy and propose new things, and then skeptics who are interested in pulling back the wild speculation. But are there positive things that philosophers can do? Absolutely there are. I think my work on inductive inference is an example of that. The notion of what is the appropriate logic of science is something that philosophers ought to be paying attention to, and I think my account of the nature of inductive inference is the correct account. Of course, I'm going to say that, and I will defend that. And I think it's actually useful for scientists to know that, because one of the consequences of the view is if you want to infer better inductively, you need to know more facts. And then finally, I should say that I don't think there's a sharp dividing line between what philosophers of science do and what scientists do. We tend to focus very much on the foundations of the science. The scientists themselves tend to be looking for the latest results. They're looking for what the new chapter 12 would be in the textbook. We're still stuck in chapter 1. But we can still do useful work there. Again, I'll talk about my own work because that's the work I know the best. In the 1980s, John Ehrman and I looked at an argument that Einstein had run known as the Hole argument, and we used that as a way to make trouble for a particular view about the nature of space and time, space-time substantivalism. We thought we were simply doing an interesting piece of philosophy of science, but it turned out to be useful in the debate between different theories of quantum gravity. So the people who work in loop quantum gravity were using it as a way to criticize what people in string theory were doing. They were saying they had neglected the morals of the whole argument as it had been brought into new work. So I think there's plenty of work for us to do as philosophers of science.
Thank you very much, John. So thank you again for joining us. It's the second time we have the pleasure to talk together. And thank you to all of you for listening.